I thought like it had crawled on.
So is it recording now?
Yeah, there's the time up in the corner.
It is awesome. Okay. Can I move this guy? Yeah.
Yeah.
Where is it going to be least intrusive? Here.
Yeah.
All right. So active transport is the movement of ions or molecules up their concentration gradient. What do I mean by up? Anybody know what I mean by up? Did you say the opposite of down?
No, I said going.
Okay, so what do we, when we talk about concentration gradient, what's the normal flow? High to low, right? So up is from low to high. Down is from high to low. So it's like, because when you think going up a hill, it requires energy. When you come down a hill, it's like an easy flow. So that's why we use the words up and down. So the movement of ions or molecules up their concentration gradient or towards the side of the membrane with a higher concentration. Okay, so this time it's just requiring, we have a situation where we want to move things against the gradient or up the gradient, and it requires some effort. We can't, it doesn't just flow that way. Remember, diffusion just flows. This does not flow. Okay, so we're going to look at this picture in just a second. Let's write a couple things, then we'll talk about the picture. So active transport happens by carefully controlling how a transport protein opens and closes to one side of the membrane or another. Okay, so we have to control that opening and closing. We have this chemical or molecule that's called ATP. Does anybody know what ATP stands for?
We had read something about it.
There it is, adenosine triphosphate. Tri means 3. Phosphate is a phosphate group. So we're going to see an adenosine molecule with 3 phosphates. This is the battery of the cell. And when ATP is hydrolyzed, what do you think hydrolyzed means? Adds water. Yep. So hydrolysis, this is the process of hydrolysis. So ATP is hydrolyzed. What would happen then? If you add water, what's going to happen? What's going to happen to that molecule that has the adenosine and 3 phosphate groups? When you add water, what happens? A phosphate group is going to pop off. So a phosphate group is removed. Remember, that's like the opposite of the dehydration synthesis, where when you where it loses the water when a group is added. This is a group pops off when water is added. So a phosphate group is removed, and energy is used from that reaction to change the shape of the protein. Okay? And then when the protein changes shape, are you with me, Owen?
Yep.
Okay. It can open to the other side of the membrane. And release the molecular ion. So that it increases the concentration on one side of the membrane and the side is the one that already has the higher concentration. So once you're done writing that, we'll take a look at this picture. Yeah, you kept up with me. That was nice. All right, so here in this picture, let's look here. I'll be moving it back that direction in a second if you still have to fill in a couple words. Notice the calcium ion. These are Ca2+. This is calcium ions, okay? Notice the calcium ion concentration is higher outside the cell than inside the cell. And normally, we would see the flow to balance it out from outside to inside, down the concentration gradient. In this case, though, that's not going to happen. We're actually going to have what's inside continue to go outside. And the way this happens is notice this ATP molecule here. This is ATP, the adenosine and 3 phosphate groups. One of the phosphates pop off and hook to this transport protein. And a calcium ion can slip into the protein. Now when that phosphate group hooks on, it changes the protein shape, and now the opposite side of the protein opens and the calcium can go out. Does everybody see that? So the calcium ion is now able to go outside the cell. This is going against the concentration gradient or up the concentration gradient. It doesn't mean physically up in the picture, but from low to high. Okay? Now the phosphate group pops off, and when the phosphate group pops off, this will change shape back to normal.
Why are the last 2 pictures?
I think it's a mistake. This should just show that it's now open, so you can draw it. Okay. This should be open. Okay, and now a calcium can go in.
So it should be like the first picture?
Yeah, it should be like a first picture. If you need to see that, you can see it's the first picture. There's also, I'm going to show you a grammatical error. We'll cross it out. Okay, so that is how primary active transport works. So why does the cell, yep, I know, why?
I didn't get the very
So the question should really say, why do cells, not why does. Why do cells need to pump out calcium? So what is the point of that?
We talked about it, didn't we? Oh, wait, no, that was cool.
Are we good, Ashley, or are you still?
That was something else that needed to go out.
So why do cells need to pump out calcium? Well, I'll tell you why. Cells, oh, that's not what I meant to write. Don't write cells. Calcium is a signaling molecule. What did we say signaling molecules were? Anybody? Bueller. Y'all don't know that joke. It's fine. One day when you're old, then you can watch Ferris Bueller. Don't watch it until you're old. Okay. My recommendation is 30. You have to be 30 to watch it. Okay, so calcium is a signaling molecule. And a signaling molecule is one that just communicates with the cell. It's a molecule that talks to the cell. It gives the cell information, and the cell knows what to do because of it. All right, so when it rushes into the muscle cell, when it rushes into a muscle cell through a calcium channel, it can signal the muscle to contract. That's a good thing, right? That's how your muscle knows what to do. Okay, now the cell has to pump out calcium using active transport to maintain a steep concentration gradient and in order for it to release the muscle contraction and relax. Okay, so, in order for a muscle to relax, it's got to get calcium out of the cell. So it has to pump the calcium out. The calcium rushes in when it wants to tell the cell to contract. That's well and good, but now it's got to get the calcium out to tell it to relax. What if it can't get it out? What happens? A muscle cramp, right? So muscle cramps can happen if cells cannot pump out the calcium fast enough. So there is a reason. We have to pump out the calcium to tell our muscles to stop working. Well, you've changed the concentration in your muscles. That's why dehydration can be problematic.
So does that mean for every muscle cell there has to be an individual calcium?
There's millions of calcium ions floating in your interstitial fluid surrounding all the cells. And that's where, when the cells are next to each other, there's slight space where the movement of these ions is around the cells. So each individual muscle cell does this job.
So a nerve signal
Yes.
has the calcium?
Yes. Yep. Nerve impulses. That's a whole, we're not there yet, but we will. Yep.
So, you know, like how if you have a leg cramp or something, people will tell you to drink milk. And I know that's rich in like calcium, but if the thing can't pump out calcium fast enough, how does having more calcium help?
Well, there's a couple reasons for cramps, and in this case, this is not the only reason. So this is one reason. This reason you'll see in that there's several things going on at the same time. So having the availability of more calcium is still helpful because it keeps that gradient steep. Because having enough outside, even if you still have some inside, if the gradient outside is steeper, that's necessary for it to have that relaxing. Because in a second you'll see that our cells create this gradient on purpose for potential energy. We'll see that in a minute. Another thing though is like dehydration. If you drink a lot of water, if you don't drink a lot of water, then the concentration is much more intense, and so it messes up the balance, the electrolyte balance, and causes your muscles to not function as efficiently. So there's lots of reasons, but that is part of it.
Is that why, like, making your like legs straight like easier for it to hold on to calcium? Like, because it says like if you get it cramped in your leg, like to straighten it.
Oh, you're just kind of forcing it to let go. You're like, because where it's contracted, instead of like going with the contraction, you're pushing against it. So that's helpful. All right. So what affects the rate of active transport? Who can tell me? What things affect the, yeah.
Temperature.
Yep. Here it is.
A plus student right there.
Temperature. Good. Okay. What else? Yep. Concentration gradient. Or instead of putting gradient, just put concentration.
Oh,
We need to tell us to already did.
I just scratched it out. Look, it's okay. Life goes on.
Concentration what?
Concentration of ion or molecule being transported. Y'all are so finicky. Okay. All right. What else? Who remembers the one from last week?
Yeah.
The number of. Yep. So the number of transport proteins available. And lastly, there's a new one.
Oh.
ATP availability.
So the like second to last picture, and it has like the P coming down. Is that like?
It's popping off.
Okay.
And so this is a duplicate picture. Once this pops off, it should look like the first picture again.
Why does it pop off? Because it's done?
Yeah, because it used up the energy in the bond. All right. Next page, sodium potassium pump. All right, so a double-sided active transport process in action. All right, so now we're looking at a sodium potassium pump. Excuse me. All right, let's write some things first this time and look at the picture again in a minute. So a double-sided active transport process in action. In the sodium potassium pump, three sodium ions are transported out of the cell and two potassium ions are transported into the cell, creating steeper concentration gradients. Sodium builds up, or sodium ions build up outside. And potassium ions build up inside. I should have abbreviated sodium that time, but I didn't. Oh well. And lastly, an ATP molecule. Remember, this is our battery. Is used up in each full cycle. And in this process, each step causes the next. So let's look at the picture and then we'll go and write it. Okay, no worries. All right. Still see what you need? All right, so outside the cell, you have a concentration of sodium and potassium. And inside the cell, you have a concentration of sodium and potassium. And normally, you would think that it would move from high to low. But in this case, both things are going to be going against their concentration gradient or up it, making those concentration gradients steeper. Okay? So we're going to be pumping sodium out, and we're going to be pumping potassium in. So notice over here we have an ATP molecule again. ATP is going to be hydrolyzed, water is going to be added, and a phosphate group is going to pop off and hook to the transport protein. Notice how 3 sodium atoms fit in here, and those 3 sodium ions are going to go in, and when that phosphate group attaches, now the protein shape is going to change and the sodium is going to go out. And now that it's open to the other side, potassium's going to come in. And when potassium comes in and the phosphate group is all used up and pops off, now the protein goes back to the original shape and the potassium is pumped to this side. Does everybody see that process? Okay, so yes.
So when there's still a K on the other side, or potassium on the other side, so does that mean another ATP has to be broken down?
No. Nope, it's just one ATP being used here. And the reason is because when the phosphate group attaches, it changes the shape to this shape. But as soon as this is all used up, then it shifts right back to how it was at the beginning. And in that process of shifting is when the things come in and go out and come in and go out.
She was wondering, does that potassium ever come through that one by itself at the top?
Where?
There's a potassium on the top.
With all the sodium.
Over here?
Yeah.
This one?
Yeah, does that one ever come through?
Yeah, if it does it again. If it does
right, but I mean,
if it was just by itself?
No, if it were to have to do the process again, would another phosphate have to be?
Yes. Okay. Yep. For each cycle, it's one ATP used. So in order for it to do it again, it would need to use another ATP. Okay, so each step causes the next. So let's write the steps out. When sodium ions enter the protein becomes more attractive to ATP. I'm so glad y'all enjoy biology so much. Then, when the phosphate group is attached, the protein changes shape. Once it changes shape, and when the sodium ions leave and the potassium ions enter, the protein releases the phosphate group. And when the phosphate group leaves, the protein returns to normal shape. So what are the results? I'm just going right over here to the right. What are the results then? The result for sodium is that it's an even higher concentration outside the cell. And the results for potassium are that it's an even higher concentration inside the cell. Again, let's correct our grammar here. Why do cells need to pump out sodium and potassium? So pump out sodium and pump in potassium. Why do they do this? You caught up to me? So the cell spends a lot of ATP doing this to create a steep concentration gradient of sodium outside and potassium inside. Why? Why would the cell create a steep gradient? Okay, it does have something to do with being easier. So think of it this way. If I want something to flow really well, say I take a little car and I put it on the ground and there's like a slight slope and the car kind of moves a little bit. But what if I take that car and I push it up a pretty steep ramp? Now when I let go of it, the car is going to run down the ramp pretty fast and go pretty far. And so we are building up potential energy in the system so that it flows better, and that flow can then be used for other cell processes. That is the reason that the cell does this. So if there is a steep gradient, the cell can open another protein channel which allows sodium ions to flow quickly in, and they use that strong flow to do other work for the cell. Does that make sense? So we're building up potential energy in the system. We put in energy and push the car up the hill so that when we let go of it, it'll roll down. In this case, we use up energy to push sodium out and potassium in so that when we release the floodgates, it flows on its own. That is a necessary process for other things like this, which we're about to talk about. All right, so then we have something called secondary active transport. This is different than active transport because in secondary active transport, the movement of molecules or ions up their concentration gradient. Instead of using energy from ATP, we're using energy of another molecule using the energy of another molecule moving down their concentration gradient. It's one way that a cell uses natural processes at a membrane to do work without ATP. So in this case, we're not using ATP. Their concentration gradient. In that, gradient. Okay, so look in the pictures here. We have sodium outside in high concentration and glucose inside in high concentration. And the glucose needs to go in, but it can't flow against its concentration gradient. It needs ATP, and we don't have any. So in this case, there's this transport protein that the sodium is going to flow from high to low. Notice the gradient is that the sodium is going to flow in. The glucose doesn't want to flow in though, but because it's going to use the fact that sodium is already going that direction, it's going to hop on board. It's going to kind of ride the freight train into the cell. So sodium comes in. When sodium and glucose come in, this molecule changes shape and releases them to the inside. And now we have sodium going inside and the glucose being brought along with it against its concentration gradient. All right, so let's put some words to this. The concentration of glucose is higher inside the cell and the concentration of sodium is higher outside the cell. The cell wants glucose to come in to use as food. But the inside it already has a higher concentration. Okay, so we have this concentration inside being higher with glucose, but the glucose needs to go in, but the cell doesn't have any energy to expend. So in order to move glucose in, the cell carries sodium ions and glucose together. Both enter the transport protein outside the cell. By carrying them at the same time, the sodium ions flow down their gradient and are powering the movement of glucose. So what are the end results? The end results are the concentration of sodium outside to inside becomes less steep. And the glucose concentration inside is increased. And then the last thing to add to your page is the question at the bottom. It says, what created the sodium concentration gradient so that this process will work? So how did we get the concentration gradient outside of sodium so high? What happened? What did we do? Yes, the sodium potassium pump from the page before, where we created that concentration gradient to be so steep. That is what allowed this process to happen. So that's what you write here. The sodium, potassium, and then y'all can go. Did I give you this osmosis sheet last week? Did I give y'all this?
Yes.
Can I have your attention, please? If you are in Mr. Stites' D group, you need to make sure that you...
Oh, yes. Please go to your D group.